These notes are on the efficiency of a binary search. All right, so in O of 1, this means that no matter how much data we increase as an input to an algorithm, it will be completely constant. And that relationship can be graphed, where x is the amount of data that we put into an algorithm, and y is the time complexity of that algorithm. And this is a constant function. All right. In a linear search, it's O of n, because for each element that we increase, the max amount of steps that need to be taken increase by the number of elements that we increase. So y equals x. This is a relationship between the number of elements in the array and the time complexity of the algorithm. Now, where do we put binary search relative to these two time complexities? We know it's not O of 1 because as we increase the number of elements in the array, it does not stay at the same time complexity. The number of steps increases. But it's also known that a linear search is much, much slower than a binary search. So the relationship has to be between 1 and n. And to figure out where it goes, consider how the time complexity of a binary search grows. So because every time we double the data, or elements, the number of steps grows by 1. Because this is the case, we know that there is some function or relationship between O of 1 and O of n that follows this rule. For every doubling, we grow by 1. Now, you might think that it's y equals 2 to the power of x, because this does show that relationship. Because for each doubling of y, x only increases by 1. But in this case, like for example, if we have y equals 4, y equals 8, and y equals 16, we get 4, we get 2, 3, and 4. But this is the wrong relationship. It's the relationship we want that's inverted. So using some simple algebra on the function y equals 2 to the power of x, we can just take the log of both sides, and then we get x equals log to the power of n, or y. But we want to put that in terms of our steps. So we need to switch x and y. And then we get the same relationship, just inverted. And this is our time complexity for binary search, is O of log n. Or actually more specifically log 2 to the n, or log 2n rather, which is between O of 1 and O of n.